Hi everybody, my name is Nick Lake. I'm a physics teacher at Cass Technical High School, a public school here in Detroit. Joining me today is Mackenzie Bundy, one of my AP Physics students.
Hi everybody.
Today we're going to talk about a fun problem I posed to my students where we calculated the temperature of May's freeze gun that it has to be in order to freeze her enemies solid. So you ready to get started?
Yeah.
Alright.
It's crazy.
The first thing you need to do when approaching problems like this is making your assumptions clear. In any science or engineering calculation, making reasonable assumptions is an important skill when seeking reasonable answers. For this problem, we are assuming the following things. Number 1, we're using Newton's law of cooling equation. In this equation, R equals this. H is the heat transfer coefficient of water, which was a tricky assumption in this calculation. Most of the common use for this parameter we found is in heat exchanges using water flowing in a pipe. Of all the assumptions, there is the greatest chance this one could be significantly off. The parameter is often estimated by dividing the thermal conductivity of water, 0.59 watts per meter squared Kelvin, by a length scale. In this problem, we use 0.2 meters as an estimated radius of soldier's torso. Initially, we got an H value of about 3 watts per meter squared Kelvin. The surface area of contact is represented by A in this equation. And for our calculation, it would be the surface area of a human body. Google tells me that people have about 2 square meters of skin. C is the specific heat capacity of water, so 4,185 joules per kilogram Kelvin. M is the mass, and for this problem, we're going to assume soldier has a mass of 90 kilograms. We're assuming that the freeze gun is freezing soldier completely solid, and we're assuming the time to freeze soldier is 1.4 seconds, as that's the time I calculated from an average of several freezings I conducted in-game. We're also assuming soldier is made of 100% water to simplify the calculation.
Using these assumptions, we get an R value of around 1.57 times 10 to the negative fifth. Taking Newton's law of cooling equation, we are setting the final temperature to 0 degrees Celsius. The temperature of the environment is the temperature of May's spray that acts as the ambient environment that the person will be exposed to. Therefore, that's the variable that we're trying to solve for. The initial temperature is being set to 37 degrees Celsius, as that's the typical body temperature of a human being. Rearranging the equation to solve for the temperature of the environment, we get T environment equals beginning temperature times e to the negative RT over e to the negative RT minus 1.
So, after plugging in all of our variables in our rewritten equation, we end up with the temperature of May's spray to be negative 1.7 million degrees. To freeze someone completely solid in 1.4 seconds, you would need an ambient temperature far lower than the lowest possible temperature, absolute zero, of negative 273 degrees Celsius.
We were not satisfied with the initial try, though. Oftentimes when studying physics and engineering, if you get a number that seems wildly off, it's important to look back and check your calculations to see where you might have gone wrong.
So like we said originally, the value we found for H was the most difficult to find. When looking back at it, we found a new value for H of 13.1 watts per meter squared Kelvin. Using the website www.engineeringtoolbox.com. There we found common heat exchanger surface combinations and selecting the water to air exchange through a copper pipe, as that seemed to be the closest to what we're trying to calculate with the heat flowing from a person to May's gaseous spray surrounding them. With this new value of 13.1, we calculated the temperature of the ice gun needed to be negative 380,000 Celsius. This value is still wildly colder than absolute zero, but it seems more reasonable than the negative 1.7 million degrees Celsius we originally found. So, to conclude, when trying to find the correct temperature, we encountered trouble finding the absolute certain heat transfer coefficient of water to air. Even with the value of H as high as 10,000, we were getting values lower than absolute zero. It just does not seem possible to freeze a person completely solid in 1.4 seconds using a sprayed air like gas. An alternative that we have not considered in this video is that instead of completely freezing the person solid, perhaps May's spray only freezes the first couple millimeters of her enemy. That seems more reasonable given our results in this calculation. And also, it might make more sense if they survive after being frozen. We'll leave it up to our dearest viewers of this video to do their own calculations for that problem though.
Thanks for watching. We hope this video has been enjoyable for you to watch and you learned some valuable lessons on making helpful assumption and calculations and how to do some fun in science and engineering problems in any experience you have. For those of us who like video games, we can learn about how fun the physics are in those games by doing real-life calculations for the amazing feats our characters are performing. An additional special thanks to my friends Thomas Roger and Paul Munn, who provided their invaluable assistance in calculating these problems. They were not able to appear in this video but deserve mention. Another special thanks goes to Brandon Smith and Big Sean for giving us the use of their studio for recording this.